Hey there, this is Verbsky back. We're going to do 10-2, sum and difference formulas. Mostly everybody likes these formulas. The book does a real good job with proof of the formula. Um, Actually, it's the cleanest version I've seen in a long time, and it's spelled out very well. If you're interested in where these formulas come from, read page 737 through 738. But we're going to try to keep this lecture short and sweet here. So here we go. Sine alpha plus or minus beta, these are two formulas, is sine alpha cosine beta plus or minus sine alpha sine beta cosine alpha. So I go sin cos alpha beta beta alpha, plus goes with plus, minus goes with minus, even though I'm not supposed to say sin cos. It's sine of alpha cosine beta. But it does sound pretty cool. Sine alpha plus beta is sin cos alpha beta beta alpha with a plus. Cosine alpha plus or minus beta is cos sin, and I go alpha beta alpha. That minus goes with plus, and the plus goes to minus. So we got this right here. Once again, the derivation is outstanding. But skip that for once. Went for a nice simple approach to the section. Now, these formulas are very important. Would I remember them? I've been burnt once or twice in my math career when I didn't know it. I remember failing a test because I didn't know one of these in grad school. So anyway, yeah, these are pretty important. But what we're going to be doing with them does seem kind of hokey, but let's play the game. Walk before you run. So here we go. Let's try to do like sine of 15 degrees, because that's not on the unit circle, only the multiples of 30, 45, 60, 90. We don't have sine 15. Let's say we wanted to know sine 15. Well, I just happen to know that that's sine of 45 minus 30. And if it has a minus, you go sin cos 45, 30, 30, 45. And with the sine formula, minus cos. Then you just look it up on your unit circle. Square root of 2 over 2. Square root of 3 over 2. 1/2. Square root of 2 over 2. Or learn them, know them, live them, breathe it. Get those down. Square root of 6 minus the square root of 2. Since they're both over 4, we put it over 4. That's the exact answer. No wonder we don't memorize that one, huh? It's like square root of 4, 2, sine 15. I have no idea. It's square root of 6 minus square root of 2 over 4, apparently. Like, what I don't like is when they do this to me. Sine of like 5 pi over 12. Well, pi over 6 is 30 degrees. So pi over 12 must be 15. So this is really 75 degrees. So I'm going to think degrees the whole time I work this problem, because whether it's sine of 75 or sine of 5 pi over 12, it's going to be the same thing. Now you got to get lucky and figure out two angles that perhaps add or subtract to 75. So it's really sine of 45 plus 30. But you should at least make me feel good and use the radian versions, just so, we get used to it. Now, sine, when you add angles, is sin, cos, alpha, beta, beta alpha with plus. And then you just look up your unit circle, sine the y-coordinate at 45. Cosine of 30 degrees is square root of 3 over 2, plus sine of 30 degrees is 1/2, and cosine of 45 degrees is square root of 2 over 2. And we get something very similar to the last answer, square root of 6 plus the square root of 2 all over 4. Once again, seems kind of hokey. Now, this is called a cofunction. But what I'm going to do is apply the cosine formula to it, and then I can actually explain what a cofunction is. It's cos, sin, 90, theta 90, minus is plus. Now the cosine graph looks like this. At 90, it's 0. So this term goes away, and sine of 90 is 1. So all this is sine theta. And they call this the cofunction identity. So they work for all 6. So let's get this in our notes now. So if you say sine theta, that's cosine 90 minus theta. And you know cosine theta, if we'd do the similar proof, is sine 90 minus theta. And tangent theta is cotangent 90 minus theta. And cotangent theta is tangent 90 minus theta. Sorry, I think I cut it off there. I just sneezed. I have a cold, if you can't tell. Secant theta is cosecant 90 minus theta. Cosecant theta is secant 90 minus theta. This author likes cofunctions. It's called the cofunction identities. What I just did was a proof to show you one. They all work out exactly the same. I can talk about graphs and shifting and flipping graphs and all that and basically prove it to you again. So, anyway, went off on a side tangent there. Humor. All right. So, what does the book have for me? I'm looking through the book and it's not doing a lot for me, except they go right into what is tangent alpha plus or minus beta. Well, that's sine of alpha plus or minus beta over cosine of alpha plus or minus beta. And then we could go sin, cos, alpha, beta, alpha, plus goes with plus, minus goes with minus, all over cos, sin, alpha, beta, minus or plus, beta, alpha, do some whole bunch of algebra, a whole bunch of identity work, just like they show in the book, and you get tangent alpha plus or minus tangent beta over 1 minus or plus tangent alpha tangent beta. We don't have the ones for secant, cosecant, and cotangent. We don't. Do they exist? Sure they do, but we don't use them. Anyway, that's your formula for tangent alpha plus or minus beta. See, plus goes with plus, minus goes with minus, but plus goes with minus, and minus goes with plus. So, let's do a dumb problem. So learn the identity. Let's do tangent 7 pi over 12. Well, I know pi over 6 is 30 and pi over 12 is 15, so 7/15ths, they're really asking tangent of 105 degrees. Whether I do tangent of 105 or tangent of 7 pi over 12, I'll have the exact same thing. Now, let's find two angles that add or subtract 105. How about 60 and, nope, 60 and 45? Yeah. So tangent is 60 plus 45, but let's grow up and use radians. Pi over 3 plus pi over 4. And that is, it is tangent of pi over 3 plus, goes with plus, tangent of pi over 4 over 1 minus, the lower is opposite, tangent of pi over 3, tangent of pi over 4. Now unit circle to me goes 0, square root of 3 over 3, 1, square root of 3, d and e. So pi over 3 is 60, so square root of 3. Pi over 4 is 1, over 1 minus copy, copy. So I get the square root of 3 plus 1 over 1 minus the square root of 3. Now, we could stop there, but traditionally in math, we multiply by the algebraic conjugate to get rid of the radicals in the denominator. Once again, I don't know who actually made that up. You'll find in calculus we're happy, we're fine with them in the denominator sometimes. 1 minus 3 is negative 2. And let me write this as the square root of 3 plus 1. It'll be easier. First 3, outer, inner, last, so 4 plus 2 radical 3. Man, this doesn't work out very good. Now I can factor out a 2, old school, and get a 2 plus or minus, plus the square root of 3 over a negative 2, which is minus 2 minus the square root of 3. Wow. The algebra was like 50 times worse than the problem. And then they do some applied stuff that we are not really focusing on just yet. But then there's the classic, the total greatest problem ever, like sine beta equals negative 7/8. And beta is in, going to be negative, let's say the fourth. And cosine alpha equals negative 4/5. And beta, oops, that'd be alpha. And alpha in the second, because cosine can be negative in the second and third. And then they're going to ask us a whole bunch of questions like, hey, sine alpha plus beta. And then you're going to go sin, cos, alpha, beta, alpha, plus is plus. Then you got 4 places to fill in, but I gave you 2. Sine beta, negative 7/8, cosine alpha, negative 4/5. That you are going to have to draw yourself a triangle. So you get yourself a beta ref. I'm not going to actually draw it in the fourth quadrant. I'm going to just use reference angle, first quadrant. And I'm going to say so. I'm going to go 7/8. 64 minus 49, square root of 15. And then I'm going to do myself alpha ref. And I'm going to go a ka, a 4, 5, 25. Oh, duh, 3. 3, 4, 5 triangle. Now, alpha's in the second, and sine goes all students. Sine is plus in the second. Cosine beta, beta's in the fourth. All students take calculus, beta's positive. Now you just look at the triangle and do your ca and your so, and you should be good. So looking at the alpha, you say sine, you go 3/5. Looking at the beta triangle, you say ca, you say square root of 15/8. And we end up with square 3 square root of 15 plus 28/40. They're both over 40, so you can combine them. Double negative makes it plus. So they could ask you any question they want. So they can even go part B, tangent alpha minus beta. Then you're stuck, oh yeah, tangent alpha, minus goes with minus, tangent beta. Now on the bottom, there's a 1, but it's going to be opposite, and then same thing as above, but only you're multiplying. So you got these spaces to fill in. Then you just got to crank them out, but you got to say TOA. So let's do the tangent alpha. Let's take care of that. Tangent alpha. Where's alpha? Alpha's in the second. And we're talking about tangent. All students take. So I'm going to get negative. Negative for tangent alpha. Now you say TOA. So you're looking at that alpha and you go TOA, you go 3/4. So tangent alpha is negative 3/4. Now we got to do tangent beta. Tangent beta is TOA, but you got to go back up and you go beta. Where's beta? In the fourth. So tangent is negative in the fourth. So you're sitting on beta and you go 7 over the square root of 15. 7 over the square root of 15 with a negative. 7 over the square root of 15. So 7 over the square root of 15, 7 over the square root of 15. Now, do you want to rationalize on the fly? Let's try it. It might kill us. Ooh-wee. Okay, here we go. Bring that back. So minus 3/4. Take away 7 radical 15 over 15 over 1 minus 21 radical 15 over 15. But this busts down into 7/5. I'm going to pull a minus out and then do that crisscross applesauce thing. So 45. But because I pulled the minus out, it's actually a plus 28 radical 15 over, I guess, 60. I'm not going to reduce that anymore. Oh, yeah, I am. What the hell? It doesn't matter. Over 1. So I can only read what I wrote. Okay, yeah. So 5 minus 7 radical 15 over 5. Then you got 45 plus 28 radical 15 over 60 times 5, or 5 minus 7 radical 15. The 5 and the 60 go 12. That 45 is 9 and 5. 28 is 4 and 7 now, nothing in common. Okay. So I get 45 plus 28 radical 15 over 12, 5 minus 7 radical 15. Now I'm fine with this, but I'm thinking we better multiply by 5 plus 7 radical 15. 5 plus 7 radical 15. In the bottom, that 12's just hanging, but you get the 25 minus 49 times 15. The top is disgusting. 45 times 5, 180. Outer is plus 7 times 45 radical 15. Inner is 5 times 28 radical 15. Plus last is 28 times 7 times 15. Totally disgusting. I give up. I could keep going. I didn't get my calculator out, guys. It's not worth it. Not worth it. Anyway, it's a classic. You need to work it, and then it turns out I'm into the exercises already. So that's great because there's 19 minutes left, 18 minutes left. I'm going to do the identities in that section because in each and every one of these sections are their identities. What's the most important section? Probably 10.1. What's the second most important section? I think it's going to be section 10.3 or 10.4. So anyway, I'm going to just pick the even problems. So 52 on page 745. These aren't as hard because it just basically screams at you, please use the identity. They go, verify this is identity. Well, I'm going to start it on the right because I can't go anywhere if it's 0. So I'm going to start on the left, and you go sin, cos, 120, x, 120, plus is plus. Take away cos, which is cos, sin, 120, x, 120, and the plus is a minus. Now, we get out our unit circle, negative 1/2 the square root of 3 over 2. Sine 120 is the y, square root of 3 over 2 cosine x. Cosine 120 is minus 1/2 sine x minus another 1/2, but another minus is plus 1/2 cosine x. Minus and minus is plus, and sine 120 is the square root of 3 over 2 sine x. Seems like I am missing something here. Okay, what did I do? So I got this one. I got this one. Did I copy the problem down right? Sine 210x minus cosine 120 plus x. Verify each as an identity. Okay. So, here finally I get stumped. I think I did something wrong. cosine 120 is the x coordinate, so negative 1/2. So let's start here. Sine 120, square root of 3 over 2 cosine x. Cosine 120 right here, that's negative 1/2 sine x. Now we go minus. So you go cosine 120, which is a negative 1/2 cosine x. So really it becomes plus 1/2 cosine x. And double negative, sine 120 is positive, square root of 3 over 2 sine x. This is not working out. I will look at it later. I don't want a whole bunch of time. So that was problem 52, page 745. They're claiming it's an identity, which is looking like it's not. It doesn't look like they're identical, unless you guys see an obvious mistake. 54. Tangent x minus y minus tangent y minus x equals 2 tangent x minus tangent y over 1 plus tangent x tangent y. All right, proof. This is tricky. I'm going to shove that minus sign back in because tangent is odd. Now yeah, that would be the easiest way to do this. This is the easiest way to do that. So if you shove the minus sign back in, which you can alternate tangent. So you get a tangent x minus y. Now if you shove that minus, it becomes tangent. But you bring the minus sign in and it reverses the signs, x minus y, which is 2 tangent of x minus y, which is 2 times, well, this is the formula for tangent x minus y. It's tangent x minus tangent y over 1 plus tangent x tangent y. Game over. That was really tricky, though. I can't say I ever made that. I don't know if I ever did that in my life, but it was brilliant. Use the property odd to move the negative back in, change it to a plus, alternate the sign. Boom. Quick kill. 56. Sine alpha plus beta over cosine alpha cosine beta equals tangent alpha plus tangent beta. Proof. Gonna start on the left. I'm gonna just jam it out. Sin cos alpha beta beta alpha plus is plus over cosine alpha cosine beta. Now you can bust up fractions. There's really just one term in the denominator because of the multiplication. If there's plus in the denominator, you can't do this. So one term in the denominator, you guys can see the cosine beta is going away. So it's sine alpha over cosine alpha. You can see the what's going away. The cosine alpha is going away. So you get sine beta cosine beta, which is the right tangent alpha plus tangent beta. Next step, 58. Tangent alpha plus beta minus tangent beta over 1 plus tangent alpha plus beta tangent beta equals tangent alpha. Ouch. Doesn't look any fun. make sure I copied it down right. It looks brute force to me. Use the formula. Let me see. If I circle like this and circle like that, no, let's just brute force it. Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta minus tangent beta all over 1 plus, let's do it again, tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta times tangent beta. Oh, crisscross applesauce. So tangent alpha plus tangent beta minus tangent beta times 1 minus tangent alpha tangent beta. This minus this over all over 1 minus tangent alpha tangent beta all over crisscross applesauce. So 1 minus tangent alpha tangent beta plus tangent beta times tangent alpha plus tangent beta all over 1 minus tangent alpha tangent beta. Now you're done this enough that you are starting to figure out that the second and fourth cancel each other out when you copy dot flop. So really, that's all we have left is tangent alpha plus tangent beta minus tangent beta distribute plus tangent alpha tangent squared beta over 1 minus tangent alpha tangent beta plus tangent alpha tangent beta plus tangent squared beta. These go away. These go away. And you got a tangent alpha and a tangent alpha. So let's factor out a tangent alpha. There's no visible 1 there. 1 minus 1 plus tangent squared beta. You got a 1 plus tangent squared equals the right. Craziness. Craziness. Was I worried? Yeah, I might have made a mistake. As you can see, the algebra is pretty much the same all the time. I'd like to stop, but there's one to go. 60 cosine alpha minus beta over cosine, oops, help write it down right, sine alpha minus beta equals 1 plus cotangent alpha cotangent beta over cotangent alpha plus cotangent beta. Now, there's no secret. There's reciprocal stuff. So, if we took a reciprocal on both sides, this would totally make sense. Because you know this is really cosine over sine is cotangent of alpha minus beta, but we don't have a cotangent alpha minus beta formula, but there it is. You know, it's really that. Now, is there a quick way to get into it? I'm thinking proof left there is no difference between the left statement and the right statement. I just kind of did a reverse copy dot flop. So if you would copy dot flop that 1 over 1 times that, it certainly would be cosine over sine, so no problem. But this is 1 over tangent of alpha minus beta, which is 1 over tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta, which is 1 plus copy dot flop tangent alpha tangent beta over 1 over tangent alpha minus tangent beta. If this is 1 plus the reciprocal Now I'm going to go crisscross applesauce, and you get cotangent alpha, cotangent beta plus 1 over cotangent alpha, cotangent beta, all over cotangent beta minus cotangent alpha over cotangent alpha, cotangent beta. All right. That was hard, really hard. My brain hurts. There's probably a better way to do it. That's why my brain hurts. All right. So, sorry guys, that's all I got. You know, once again, this section's relatively important, but the next section coming up is like super important. So, you know, just get the stuff down. You only gave you like 3 formulas, and they're just having you play with them. The whole identities, the last 5 I did, are just always seem kind of dumb to me. They don't really help you in your calculus life, other than if you forget the formula, it hurts you. Anyway, that's it for today. I'm done with this lecture.